Hello students, welcome to EPG Pathshala. I am Mahavir Singh from Physics Department, Himachal Pradesh University, Shimla. Today we are going to talk on module Elementary Excitations under the paper Solid State Physics. So students, let us see what we are going to learn in this module. Learn about the atomic and nuclear fluorescence. We will discuss here what is atomic fluorescence and what is nuclear fluorescence. Learn about the recoilless emission and absorption. Then we will also know how electric and magnetic exchange interaction play the crucial role so as to involved with the Mossbauer spectroscopy. Then we will also discuss the effect of these interaction, how they affect the nature of the material. Then we will also learn about close connection between this Mossbauer spectroscopy and the magnetism. So first, as we know that before Mossbauer spectroscopy, it was only atomic fluorescence. Atomic fluorescence means it was not because of recoil. Because of recoil, it was difficult to get fluorescence at nuclear level because of recoil. But during master degree, Mossbauer found a unique phenomena. He gave his breakthrough research that by putting nucleus in a lattice, by doing so, he increased the mass of the system. And as we know that recoil energy is inversely proportional to mass, so by doing this process, whether it is with emission or whether it is with absorption, he increases the mass. But here, as we see in the free system, in the given figure, this is a free case. Here, if we take a free case of nucleus, say for example nucleus whose mass is very small, so recoil is large. So in this case, due to this large recoil, this resonance is difficult and fluorescence is difficult.
So let us discuss with the basic principle associated with the Mossbauer spectroscopy. Before 1958, nuclear fluorescence was not possible because of recoil in a free nucleus. But after Mossbauer discovery, he put the nucleus in a crystal so as to reduce the loss by increasing its mass. As we know that recoil is inversely proportional to mass. So basically this was the major breakthrough done by Mossbauer by putting nucleus in a solid crystal so as to reduce the loss. This Mossbauer spectroscopy is directly linked with nuclear resonance fluorescence, and it can be also compared with, as we imagine the jumping from a boat to a shore, that imagine that distance from the boat to shore is the longest you can possibly jump. If boat is floating in water, you will fall short because some of your energy goes into pushing the boat back. If water is frozen solid, however, you will be able to make it. So if we compare this concept with the nucleus, so if we have a free nucleus, there is recoil as in the case of boat. But if boat is moving on the frozen solid, then there is less recoil. And similarly in the case of nucleus, if we fix it with lattice, then there is less recoil. So Mossbauer spectroscopy is basically linked with recoilless emission and absorption, and there is well defined resonance based upon this Doppler effect, and Doppler effect is also highly useful by using this concept in Mossbauer spectroscopy. Mossbauer effect therefore demand us the deep penetration of gamma radiation into condensed material or substances, then small relative width of absorption and emission lines, and high spectrum parameter sensitivity to the internal and external factor for the substances to be investigated. As we know from Heisenberg uncertainty principle that product of error in energy and error in time is greater than or equal to Planck's constant. So basically this delta E is the inaccuracy in measuring energy and delta E is the time interval disposed to the measurement of one energy level. So basic energetic nuclear state as delta T approaches to infinity as delta E in the ground state approaches to 0. And in the excited state delta T is not equal to 0 as delta E in the excited state is greater than or equal to Planck's constant divided by this tau in the excited state, which is the natural line width. So basically natural line width is up due to the existence of this Heisenberg uncertainty principle. So basically due to this natural line width, whether it is in the absorption or in the emission, so it is also taken into account by doing this Mossbauer basic principle. There is clearly comparison as we go through this table selected action parameter in compared with atomic fluorescence and nuclear fluorescence. There is clear cut difference in terms of energy, in terms of line width, in terms of this tau, and whether we take the nuclear state or whether we take this atomic state. So basically if we compare these two results, so there is clearly mentioned that in atomic fluorescence the observation is good, whereas at nuclear level the observation is difficult. So basically nuclear fluorescence is a really tough task to achieve. So Mossbauer was the main person who did this nuclear fluorescence, and afterward this resonance nuclear fluorescence was possible and it was highly useful in every branch, whether it is basic science or medical science or forensic science or other whether it is in geological area or other areas. It was highly useful because of this existence of nuclear fluorescence.
So Mossbauer basically what he did, he put the nucleus in a crystal lattice, and by doing so he increased the mass of the system, and as we know that recoil is inversely proportional to mass, so he reduces the loss, and he got the major breakthrough by getting the nuclear fluorescence, and on this breakthrough he got the Nobel Prize. And after this due to this nuclear fluorescence, Mossbauer spectroscopy is one of the important spectroscopy, especially in the magnetic area. And in this spectroscopy, this recoil free absorption and emission of gamma quantum. So in this spectroscopy, this Mossbauer Lamb factor, which is exponential minus expectation value of square of x and square of lambda square, this recoil free factor is very, very important, and this we can calculate this experimentally. So this factor is very important as far as this the authenticity of this spectroscopy is required. So this recoil free factor is very important experimentally and technologically also. Now this is also interesting point to discuss here. How many element we can use for Mossbauer spectroscopy, which kind of photon we can use for Mossbauer spectroscopy. As far as almost Mossbauer has been tried over 100 isotope. It is well shown in periodic table, all red are used for Mossberg spectroscopy. So, but out of these 100, mostly 90% is used for iron purposes. So Mossberg spectroscopy is used for those area where whether it is iron base or iron or mixed iron based compounds, and for magnetic purposes it is iron. Also in semiconductor cases, tin has been also used to a quite extent. Then also in for superconducting purposes, europium is also used, but experimentally it has been tested for more than 100 isotopes, and all these isotopes they are radioactive. So this technique for this technique a lot of precautions are required because of this radioactive nature of the element. And especially if we take the example of this iron whose half-life is more than 270 days, so it can be used, and its strength can be calculated on the basis of its activity. So we can take 25 millicurie or 50 millicurie, that depends upon the requirement of the researcher. So as I discuss that it has been tested mostly for iron. So for iron it is cobalt 57. When cobalt 57 decay to iron by beta decay, we got the excited state of iron 57. So when iron 57 from excited state to ground state, there are three possibility. 11% it goes from excited to direct ground state, and 80% possibility it come from excited state to first excited state. But there is 9% possibility which we called the probe, whose energy is roughly about 14.4 keV. So for Mossberg spectroscopy, this arrow which is shown in the figure, this arrow demonstrates this energy is required for to probe the for Mossberg spectroscopy. So this is also very important question here, that if we are using iron as a source for Mossberg spectroscopy, so we have to filter this energy. We have to choose this energy that is 14.4 keV, which act as a probe for Mossberg spectroscopy. Say for example, if we can't filter the energy, then we can't receive the resonance fluorescence. So this is also very important, that we have to select this particular energy for the Mossberg spectroscopy. So as I discuss Mossberg isotopes, there are approximately 200 nuclear transition with parameters suitable for the application in Mossberg spectroscopy. Transition energy less than the energy of elastic atomic bond in a lattice, and lifespan of expected nuclear level within the range of 10 raised to minus 5 second to up to 10 raised to minus 13 second. And so for 110 isotope have been examined. Their application in Mossberg spectroscopy is as follows. As per this data, UNC data, April 2007, these are the publications, and as we can see that mostly 64% papers are from the iron base, and 3% of europium base for superconductor, and then 18% of tin base. As I mentioned, mostly Mossberg spectroscopy has been used for magnetic area, semiconductor area, and superconducting area, and 106 transition. There are also 13% publication for other areas, which covers almost 110 isotopes. So these are the comparison of properties of the most applied isotope of, as I mentioned, this iron iridium. This is a host. So iron host and radium host, whose energy for iron, as I mentioned, 14.4 keV is the threshold which act as a probe, and 1 to 9 keV for iridium. And this, as I mentioned, power factor, Mosbor recoil free factor, it is 0.91 and it is 0.06. So this is also very important. These two, energy and this recoil free factor, these are two important parameter to authenticate this spectroscopy.
analysis of Mossbauer spectra. As we know that Mossbauer spectroscopy has an extremely fine energy resolution and can detect even very minute changes in the nuclear environment of the relevant atoms. Whether it is electrically linked, whether it is magnetically linked, whether it is monopole, whether it is dipole. So basically, if there is change in an environment, then Mossbauer spectroscopy can detect that minute changes. Typically, there are three types of nuclear interaction which we can observe in Mossbauer spectroscopy. One is isomer shift, which we called a chemical shift. Another is quadrupole splitting, and third one is hyperfine splitting. Sometimes this hyperfine splitting is known as Zeeman splitting. In isomer shift is linked with monopole interaction. That is, this isomer shift is linked with the s electron charge density. So if there is change in an environment in the core of the nucleus, then immediate nucleus is s electron density. So basically, if there is change in s electron density, which is further linked with covalency or oxidation or bonding, so it is basically linked with isomer shift. So isomer shift is very important Mossbauer parameter, which is directly linked with covalency, oxidation or nature of bonding. Then second one is quadrupole splitting, which arise due to change in the shape of nucleus because of the existence of electric field gradient. So if there is electric field gradient, if there is interaction between nucleus and electric field gradient, then there is change in the shape of the nucleus, and this Mossbauer peak shift into a doublet. And if there is no quadrupole splitting, then nucleus in the observed sample is spherical in shape. But if there is quadrupole splitting, whether it is positive or negative, then nuclear shape is either prolate or oblate. Then third parameter, which is also very important, that is hyperfine splitting. It is because of interaction of magnetic field, with the nucleus, magnetic moment of the nucleus. So because of this hyperfine interaction, peak is shifted into 6-line peak. As it is well shown in figure, the 6-line peak, if we see this figure, there is 6 doublet in the ground state and 4 line splitting in the excited state. So basically, if we take into account isomer shift, quadrupole splitting and hyperfine splitting, then we have well defined sextet, and because of these three important interactions, we can understand the nature of nuclei which is under investigation. Now, typical method evolved with this Mossbauer spectroscopy. In Mossbauer absorption spectroscopy, solid sample, sometime it is in powder form, sometime it is in thin film, is exposed to a suitable beam of gamma radiation. Now, this is important. Why I am telling suitable beam of gamma radiation? Because, say for example, if we are using iron, for iron this gamma ray photon have different energy spectrum, but for this Mossbauer spectroscopy we select only particular energy which we called Mossbauer probe, which is 14.4 kilo electron volt. So basically, if we filter out and we select some specific energy beam of gamma ray, then we can observe this resonance. Otherwise, there will be no resonance and it will be difficult to do this Mossbauer spectroscopy experiment. And detector measure the intensity of the beam transmitted through the sample. The atoms in the source emitting gamma rays must be of the same isotope as the atoms in the sample absorbing them. So this is also very important, that there must be similar kind of atoms in source as well as in the sample, which is absorbing sample. If the emitting and absorbing nuclei are in identical chemical environments, the nuclear transition energy would be exactly equal and resonance absorption would be observed with both materials at rest. The difference in chemical environment, however, causes the nuclear energy level to shift in a few different ways in terms of electric and magnetic hyperfine interactions. Although these energy shifts are tiny, often less than micro electron volt, the extremely narrow spectral line width of gamma rays for some radionuclides make the small energy shift correspond to large changes in absorbance. To bring the two nuclei back into resonance, it is necessary to change the energy of gamma ray slightly, and in practice this is always done using Doppler effect. So basically Doppler effect is also useful by making this experimentation of Mossbauer spectroscopy. So during Mossbauer absorption spectroscopy, the source is accelerated through a range of velocities using linear motor to produce Doppler effect and scan the gamma ray energy through a given range. Typical range of velocities, say for example iron 57, may be plus minus 10.047 millimeter per second, and 1 millimeter per second is equal to 48.075 nano electron volt. So in resulting spectra which we observe on the screen, gamma ray intensity is plotted as a function of source velocity at velocities corresponding to resonant energy levels of the sample. A fraction of gamma ray are absorbed, resulting a drop in the measured intensity and corresponding dip in the spectrum. So number, position, intensity of the dip, which we call peaks, provide information about the chemical environment of absorbing nuclei and can be used to characterize the sample. And those change in the chemical environment is further linked with isomer shift, quadrupole splitting and hyperfine interaction, as we discussed in the previous slide. Applications of Mossbauer spectroscopy. Mossbauer spectroscopy is unique in its sensitivity to subtle changes in the chemical environment of the nucleus, including oxidation state changes, the effect of covalency on a particular atom, and the magnetic environment of the sample. It has been especially useful in the field of zoology for identifying the composition of iron containing specimen, including meteoroids and moon rocks. Because of high precision and resolution, Mossbauer spectroscopy is highly useful in forensic science for fingerprinting. In situ data collection of Mossbauer spectra has been carried out on iron-rich rocks on the Mars. So basically spectroscopy is highly useful. It can be used in space, especially on rocks on the Mars. Another significant application of Mossbauer spectroscopy is the study of phase transformation that occur in iron catalyst during Fischer-Tropsch synthesis. While these catalysts initially consist of hematite, during reaction they are transformed into mixture of magnetite and several iron carbides. So basically detection of these different kinds of iron base compounds is possible by using this spectroscopy. The formation of carbides appears to improve the catalytic activity. However, it can also lead to the mechanical breakup and attrition of catalyst particles. This can cause difficulties in the final separation of catalyst from the reaction product. So Mossbauer spectroscopy has also been used to determine the relative concentration change in the oxidation state of antimony during the selective oxidation of olefins. During calcination, all the antimony ions in antimony containing tin oxide catalyst transform into the +5 oxidation state. Following the catalytic reaction, almost all antimony reverts from +5 to +3 oxidation state. This Mossbauer spectroscopy is highly useful by studying the all semiconducting behavior of this antimony. So significant change in the chemical environment surrounding the antimony nucleus occur during the oxidation state change, which can easily be monitored as an isomer shift in the Mossbauer spectroscopy. Synthesis of ferrite, sometimes ferric convert into ferrous during the sintering process. So if ferric convert into ferrous, that deteriorate the magnetic character of ferrite. So basically quality of ferrite is judged from the ratio of ferric and ferrous. If ferrite sample consists of more ferrous, so it is inferior ferrite. If our ferrite sample consists of maximum ferric ion, then it is good quality ferrite material. So the Mossbauer analysis, we can find the ratio of this ferrous and ferric. More recently, Mossbauer spectroscopy has been instrumental in developing the understanding of structure and function of iron containing enzyme and the model complexes synthesized to mimic the functions of these enzyme. So basically this Mossbauer spectroscopy nowadays is highly useful in biological areas also by studying the various kinds of enzyme which consist of iron. So it is clear here that this Mossbauer spectroscopy, when we are looking in the application point of view, this Mossbauer spectroscopy is a multidisciplinary area. Whether it is chemistry, chemical, whether it is basic physical science, whether it is biological science, or whether it is medical science, it is very useful technique. But unfortunate part, it is less known to the scientific community. It is not that popular technique. It is a rare technique available especially in Indian context.
So, so we conclude in this module that we came to know that what is the difference between atomic fluorescence and nuclear fluorescence. So after this discovery, nuclear fluorescence was possible, and due to the existence of this nuclear fluorescence, it is used for iron based compounds, semiconductor based compounds, and superconducting based compounds. And there are also we also discuss about recoil free factor, which is very important experimentally. Then we also know the interaction whether it is isomer shift, which is linked with the s electron charge density, about covalency, oxidation state. Then quadrupole splitting is linked with the shape of the nuclei, whether it is spherical, non-spherical, oblate, fluorite. Then we also discuss about the magnetic hyperfine interaction, which is also linked with the spin orbit coupling or whatever it may be. But as far as this Mossbauer spectroscopy is concerned, we require a source, different kind of sources. Test is more than 110 source, different isotope. So it is one is a source, then another is a drive system, so as to drive this source in because that is the condition as posed by Doppler effect. So Doppler effect is also very important into consideration. Then there is also requirement of detection. There is a well-defined detection system where we use the proportional counter. So we have a source, we have a absorber, then we have a detecting system, then we have a drive system, then multi-channel analyzer system, which can detect the gamma photon after resonance, and through multi-channel analyzer we can visualize the spectrum, and that spectrum we can calculate the Mossbauer parameter by using well-defined software. Thank you.